Is this good position?
A bit where in...
More like this, right? Oh, it was you who made that video. I see, okay. Well, I think that mathematicians learn this stuff at some point. And I learned it at some point. And then you kind of forget. So you kind of put it in a box somewhere, and you put it in a closet, and you kind of you classify it under stuff which you have already understood. But I think actually we don't really fully understand what's happening here. Let me recall what we're talking about. 1 plus 2, and so on. And the question is, what is the answer? Well, at first, of course, you say there is no answer, or the answer is infinity. And we say that because this series is what we mathematicians call a divergent series.
Blowing up.
It's blowing up. You get larger and larger. So there is no sense of getting closer to anything.
So traditionally, what do we do with the divergent series? We just ignore them.
We just ignore them. We just throw them away. But the question is whether this is the right approach, whether there is actually something we can say about such a series which is meaningful. In other words, can we assign a value to the series which is meaningful?
Professor, is it not meaningful to say that it blows up and goes to infinity? Is that not meaningful?
It is meaningful in the standard context of such series. The way you can think about this is as follows. Think of this, okay, so we have to resign to the fact that it is infinite somehow. But imagine this whole series as a kind of this huge lump. But what if there is a way, what if there is sort of a nice scalpel which will allow us to surgically remove infinity, kind of a bad infinity out of it, and then keep kind of a finite part? And then we would say, we will assign that finite part as the true answer for this infinite series. Now, we have to realize that that may not be possible for any divergent series. For example, you could do something like 1 plus 2 plus 3 plus 55 plus 47 plus 6 plus 7 plus 8 plus something, so kind of like a random infinite series which blows up. It will just blow up. There is no reason, there is no hope or expectation that there would be a way to assign a meaningful value to it. But this is a very special series because you see, it's very regular, kind of like 1, 2, 3, 4. We are actually taking the sum of all natural numbers without any gaps, including each of them exactly once. And what's interesting is that this kind of sums pop up all the time in many different branches of mathematics and quantum physics. Mathematicians have thought for a long time about trying to develop a theory in which one could actually make sense of this. And nowadays, we have such a theory. And within that theory, we could oftentimes we can say that it is meaningful to think of this sum, or more precisely, of that sort of finite piece after you remove the infinite part, that sort of a regularized sum. Maybe we should make a distinction between sort of a naive sum when it just blows up to infinity, and a kind of a regularized sum, where this regularized sum actually turns out to be this minus 1 over 12.
Oh no, minus 1 over 12.
Minus 1 over 12. So you see, it's very counterintuitive, right? Because it's actually a negative number and you are summing up positive numbers. So it certainly is not the result of summation of these numbers. It is something else. But what is it? So mathematicians have developed ways to come up with this minus 1 over 12. And actually the first person to talk about this was the great mathematician Leonhard Euler. He was born in Basel, in Switzerland, but spent also a lot of time doing his research in Russia, in my home country. Leonhard Euler was a kind of a mathematical outlaw, a kind of a mathematical gangster. He did things which were unlawful and illegitimate. And in particular, he allowed himself to manipulate with infinite series like this. In other words, he was trying to guess what could be a possible way to assign a value. And in the process of trying to assign values to this series and other similar series, he actually came up with the right answers, which were justified later by other mathematicians, for example, Bernhard Riemann, but that was a German mathematician, but that was like 100 years later. So it seems that Euler was way ahead of his time.
You can get to minus 12 in more than one way.
That's right, in more than one way. So Euler get to minus 1 over 12 in a particular way. Riemann explained later, gave a rigorous theory using his zeta function, a theory which involved things like complex numbers. So something which was not yet fully developed at the time of Euler, although a lot of this already existed, and Euler himself was considering complex numbers. But also there are other ways. We now know other possible ways of thinking of how to isolate this finite part in this infinite series. Euler was motivated by some questions, and in the process he not only studied such sums. Here's an example of what else he studied. He also studied things like 1 cube plus 2 cube plus 3 cube plus 4 cube. That seems to diverge even faster than this one, right? Because you're now taking the sum of cubes, you see. And so again, within this context of divergent series, if you just approach this the way we approach it when we study first year calculus, definitely this blows up, definitely divergent. This is infinite. It's infinite. The answer is infinity, period. There's no way around it. But Euler allowed himself to do some manipulation with such series and came up with a different answer, which was I don't remember exactly, but I think it was 1 minus 1 over 120. I don't remember exactly. I think it was that was the answer. He also, you might ask, why did I skip squares? Actually, you can do that as well. But the answer is even more surprising. You actually get 0 within that scheme. And so on. So he was actually studying all possible integer powers, by natural numbers. Like here, this you can think of this as 1 to the first power, 2 to the first power, 3 to the first power, and so on. Here, these are the squares, the cubes, and you can do the fourth power, and so on. And so the funny thing happens that for all even values, you actually get zeros, and for odd values, you get some rational numbers.
On the original videos, everyone got really upset and said, you cannot do this with divergent series. Are you saying you can? And you're saying they broke the rules, and then you're saying they did it. What is the rules here?
Well, the rules, it depends, rules within which context, okay? So let me ask you, to illustrate what I mean by this, let me ask you a question. Does the square root of -1 exist? Come on, Brady.
Well, I know we call it I, and we have these imaginary numbers.
Right.
But
does it really exist? Does it exist? Does it make sense to speak of a square root of -1? One possible answer is that absolutely not, right? Because if we think about real numbers, we know that the square of any real numbers is positive. So the square root of a positive number is well defined. Square root of 0 is also well defined, is 0. But there is no square root of a negative number. So we can stop there and say square root of -1 doesn't exist, and anyone who uses square root of -1 is an outlaw, right? And because that's not legitimate. These are some dirty tricks. But actually we now, and that's how people viewed it for a long time. But actually now we understand that there is a rich and consistent theory which includes the square root of -1. That is the theory of complex numbers. And this theory provides us with a much more interesting, much richer context, much more fruitful context, in which, in fact, we could solve a lot of problems about real numbers. So, in other words, we have to go outside of the realm of real numbers, oftentimes, to get the best, most optimal, or sometimes the only possible solutions about real numbers. So, it is in that sense that now no mathematician in their sort of right mind would say the square root of -1 does not exist. Yes, it exists in the sense that we can add it to real numbers. We obtain a well-defined numerical system, which is called complex numbers, which is just as legitimate as the system of real numbers.
Are you saying that manipulating a divergent series is in the same category as that?
Well, I would say that's a good analogy, because it shows that sometimes there are different contexts in which you can discuss different things. So in the case of square root of -1, there's a context of real numbers, where square root of -1 surely doesn't exist. Or there's a context of complex numbers where it does exist, and it's actually very useful. And likewise here, there is a sort of obvious context of the rules of analysis, the rules of calculus, the rules of infinite series, in which none of the series are well defined. And therefore, all the manipulations we do with such infinite series are not well defined. But then there is another context in which we replace the series by their sort of regularized values. And I really like to think of these regularized values as sort of like, removing imagine like a piece of gold which is surrounded by this infinite amount of dirt, and you kind of throw away this dirt and you're left with this little piece of gold. So what I'm trying to say is that each of these infinite series contains inside, it seems, this little piece of gold. And then we can say, well, that little piece of gold is the value, is the true value of that infinite series. And then the rest of it is kind of useless and we can just throw it away. If you say that, and there is a rigorous mathematical framework for doing that, then some of the manipulations, in fact, all of the manipulations that Euler did become legitimate. Because what you're doing is you are kind of carrying with you those sort of valuable pieces on each side of the formula, as well as those infinite things, and you can throw the infinite things away, and then whatever relations you find between the infinite series will also be the valid relation between those valuable pieces.
Professor, it seems my understanding of mathematics is it's very rigid and rigorous and it's never arbitrary. How can you just throw away dirt and keep the gold? It doesn't seem.
That's right.
Rational.
Well, in a way, it is. It's a great question because I think that it's a misconception to think of mathematics as this sort of linear process where we are only doing things which are legitimate, which are allowed. If we were doing that, we would never discover square root of -1. We would never even discover square root of 2. For a long time, people did not believe that square root of 2 actually was a legitimate number because it cannot be expressed as a fraction. Right? It cannot be expressed as a fraction. And for a long time, people thought the only legitimate numbers were fractions. Right? So actually, every once in a while, there are people like Leonhard Euler, like Riemann and others, who actually, Ramanujan is another example, who kind of jump into the abyss of the unknown and break the rules and try to kind of push the veil over the unknown and try to understand more. And sometimes they are actually doing something maybe illegitimate at the time, maybe they're ahead of their time. But one thing which is important in mathematics is that we can never leave sort of these things as loose ends. We have to find a justification. So you're right, mathematics is rigorous. And at the end of the day, we are looking for a rigorous justification, a rigorous explanation of everything. In other words, we are not content with just saying that there is some magic over there. There is magic, but we always want to explain it. And that's what has happened to some extent with this series. The work of Riemann gave us a tool to analyze this sort of the golden parts of this infinite series. And, but I still think that the last word on the subject has not been said because we still don't fully understand, at least I don't fully understand, why every time such a series pops up in mathematics or in physics, we get the right result by replacing it by precisely that value or by this value for this one. In physics, for example, this kind of calculations are done all the time. And in fact, maybe it is the best kept secret, maybe in physics, in quantum physics, is that most of the calculations that physicists do today are like this, that the answer they get is infinite at the outset. On the face of it, it looks infinite. But they find ways to assign meaningful values to this infinity, so to speak. And it is really, I think it's a good analogy to think about it, is kind of like surgically removing some kind of infinite part, which is redundant and superfluous, and throwing it away and replacing the answer with this finite remainder. And the interesting thing is that in physics, physicists are still kind of waiting for their own Riemann to come and sort of and to justify these calculations. But they've been incredibly successful in getting results which they can then test experimentally. And some of this has been tested with an astonishing degree of accuracy.
Is it a sum? Is assigning the value the same as the sum? Is that where things have gone wrong? Or where things have become confused?
I would say it's not exactly the sum because it's the exact sum, as you see, it blows up. It is infinite. It is a kind of regularized sum. But I am surprised, for example, why is it that every time we encounter such a sum in mathematics, and there are so many places where we do that, where we do encounter this kind of sums. Every time we encounter these sums, we always have this sort of reactions like, oh, we should replace it by -1/12. And every time we do that, we get the right answer. And then maybe later on, mathematicians find an alternative way. Because in mathematics you can often, there are different approaches, there are different solutions. So you have a problem, but you can solve it in many different ways. So that's an indication, I think, that if we come up with such an infinite sum, it's an indication that maybe we're doing something not quite right. We're kind of applying maybe kind of a naive approach. But interestingly, every time it happens, if we replace it by minus 1 over 12, we get the right result. And then later on, we can justify and choose a different route and have a different explanation. So what does it mean? Does it mean that in some sense, there is a context in which this sum, this infinite sum, is mysteriously minus 1 over 12? I'm not sure. It's clearly there is something in there which we still don't fully understand. For now, our understanding is that minus 1 over 12 is this sort of golden part, is this sort of finite part in this infinite lump, which you get by throwing away some infinite dirt.
I'm going to give you an astounding result.
Astounding.
An astounding result.
So I'm just going to write down a little sum, and we're just going to see what answer it gives. 1
plus 2
plus 3
plus 4
plus